So we had stopped at the equation or the solution of the wave equation on a semi-infinite string, right? Now, obviously, the next step should be to put the other end condition, but before that, a small segment I would like to have on the rigidity of the end which you put. We said that it is rigid, right? In the previous case, we said it is rigid, and we then derived how it will be, the wave equation. But then, if it is not completely rigid, if it is slightly yielding, then what will happen? So once it's a small segment, so we should know that because no condition will be completely ideal as we discussed. Even when we go to acoustic, the same thing. The walls will not be completely rigid. The walls will have they will yield as the pressure wave interacts with them. Okay. So to understand that a bit, this thing will be useful. So what we are saying is now this the peg which we have used is a bit yielding, and then that flexibility we will represent as a spring, mass and damper system, right? Because that means this will have a stiffness, this peg, this rigid end will have a stiffness, it will have a damping capacity, and it will have its own mass maybe. Okay. So then what and if you look at the shape of the string now, the force which the string acts on this peg will depend on the slope at that location, right, the vertical thing. So we are saying that in fact this we are representing as a sort of I'll change this or so maybe it's like this. So there is a mass, there is a spring, and there is a damper. It's like this. Okay. I mean, depending on the rigidity, all these three factors can be changed: the spring, mass, effective spring, constant mass, and damping. Okay. Now, and if now that means the tension times the partial of y with respect to x, okay, at 0 at t. So this will be the forcing function on that system, right? And what will be its so this is in a way the excitation which is coming onto that system, and what will be its reaction, sort of mass times it's like, right, and at x is equal to 0 plus say stiffness times at x equal to 0 and k times y, right. Now if you equate these two things, because this is the force which is coming onto this system, You can think like that, right? Now, if now we assume that I'll take these things a bit. So, what I am saying is, suppose you take y x of t. Now, we will again write, say, the general form of what will happen to the solution. So, I will just write it and then explain why I am specific form I am writing. Okay, I will take this as the solution. Now, phi, so see, this is a very general trick which is always used. Is suppose you have a function of x. Okay, if you know the snapshot in a way of the function, then you can write how it will move by changing it to x minus ct, right? It's being uncomfortable in sitting. Yeah. So that's one of the way, but then another way is, if you know that in suppose in this case we know or we want to write everything in terms of the motion at x is equal to 0, right? So then what you do is, if you know how at x is equal to 0 is fct, if that is changing, then you can do you can again write the movement of the wave by writing ct minus x or plus x, depending on which direction it will move. Okay. Why it is possible, why you are able to do that? Again, remember that discussion of a person who is seeing at a given location and the person who is taking snaps. Now, their curves will be very similar and they will just change by changing this transformation. So, this is the snaps perspective, this is the person standing at x equal to 0 perspective, and whatever he is seeing there, it moves with respect to space also. So, by just changing like this, you can express the same wave being moving. Okay. So, that is how it is generated. This trick always you can use. In fact, we will be using this many times in future. And here, because this equation, this equation is there is an inequality. Okay, this equation is valid at x is equal to 0 only. This is not valid anywhere. So, if we call x axis this direction, so at x is equal to 0 only this is valid, this equation, and that is why we started in this form, so that we can write the next equation easily, which I am going to write. Okay. So, now you can think this as now as soon as you write like this, you should be able to see in which direction it moves. This moves in negative direction, x plus ct, and this moves in positive direction. You can think this of this as g of minus of x minus ct also, and any any function with an argument x minus ct means it moves to the right. This minus doesn't make any sense, it just flips it. If you take any function, it just flips it about the y axis, it does nothing. But movement is dictated by this form of x minus ct or x plus ct, right. So, this function will be moving to the right. Any queries or fine? Okay. Now, and this one is valid for x greater than equal to 0, okay, because this side there is no solution for that, and these two functions will have physical meaning on the right side semi infinite string. Okay. Now, what you can do is, if you take f z and g z, where z is ct sort of thing, okay, not because you are talking about that x equal to 0 point, and so what this means is the same function, the argument is just z, if you write like that and substitute this here, because this has to satisfy this at x is equal to 0, and when x is equal to 0 this becomes fct sort of thing and gct, which we have just denoted by z for making it short. There is one more reason, I will come to that. You will get the equation, it is a long equation, I will just copy it here, be mc square e square g over d z square plus rc plus d dg over dz plus kg. This is for the g, and the other side you will get minus mc square plus rc minus t df by dz plus kf. So, this is what you will get if you substitute these equations, or I will just write that, okay, y z is equal to this, you know, fz plus gz, which is true for x is equal to 0. And please note that that is why these things have become instead of partial, the normal differentials, because now it is just a function of time, x has vanished. And so, if you can solve this equation, now what is the benefit? Just one moment, you can see here. See, this part is the known part, right? So, means this is the left moving wave. So, that means somehow you will define that to be, say, like this. Suppose this is your fz, means at not x equal to 0. Okay, I'll say ct plus xl, right? Okay. At t is equal to 0, suppose this is the shape. Now that will move this side. So this is the known function with which you will start, but like in the previous case, now we don't know this, how it will be reflected back, how the right going wave will become. So that is why we are trying to solve for this, knowing this. So that's the idea. Okay. So this will be known. So if you go to this side is completely known, because you know the function f with which you gave the initial condition sort of. Okay, and this side is the differential equation in G. If you can solve for this, then you can you know the function g of z, which means g of ct, and then you can write from here, just replace, I am not writing equal, you will just replace g with ct minus x, and that will be the way with which it will move forward, right. So in that way you can calculate, and this can be solved because now everything is starting at some t equal to 0, hai na? And before that no wave actually was reflecting, if you consider that assumption, so that there is at least a small distance here, so that some finite time it takes before this wave hits this end, so that you can use the Laplace transform here to convert it into Laplace. It will become a GL in Laplace, and you know how to solve this in Laplace domain. Just transform into Laplace domain and get GL in terms of FL or S, sorry, means GS if I say, in terms of Fs, and then just take the inverse Laplace to get the GT. Okay. So that is how, so that's the basic idea with which you can actually solve the situation where the end or the boundary condition is not properly rigid, it is having a flexibility. Okay. Okay. Any queries? Okay. So we will stop here for this segment, and we will see in the next segment.